Today, the recording will be available, as will the slides. This is good because Paul will be using some web resources, so there'll be links to those. Right, so if you used Zoom meetings a lot before, you may have used the chat. We're not using the chat today. Instead, there's a Q&A button at the bottom. So you can use the Q&A to ask questions during the webinar if you like. I should be able to field some of those, but many will require an expert answer. So Paul will answer those together near the end. We're expecting today something like 90 minutes of content. Most of that is the webinar from Paul. That includes a cut to his research lab, which you may have just seen if you were here a little early. There'll be a short quiz about 45 minutes in. This is just for fun, so don't stress about it. And I can talk about the questions and we'll have a discussion about the answers. And then a little bit more from Paul and then a Q&A at the end. So I think we're ready to go. I'll now hand over to Paul Meredith. Here he is. Thank you, Paul, whenever you're ready.
Thanks, James. Good day, everyone. Nice to see some healthy participant numbers. And I'm looking forward to speaking to you for the next hour or so, hour and a half or so, about some really very important things that I know many of you are very concerned about and do a lot of thinking around, as do I. So in the background of my picture here, before I go to my my presentation, you'll see some solar panels, and you'll also see some sheep. And believe it or not, sheep and solar panels are quite closely linked, as we're going to hear throughout the webinar. I would just reiterate a few things. We'll have a Q&A at the end, so keep your intelligent answers and questions coming through to us. There'll be plenty of web resource, some interactive stuff going on. And if we can manage it, we've got a live cut to our special laboratories down in Swansea, where we'll be actually making some solar cells to show you, so that should be quite exciting. Okay, so I'll start the content now. And I'll share my screen with you. And here we go. So as James said, we're from Swansea University Physics Department. This is the latest in a series of webinars that we've been given over the summer. It's a means for us to communicate with our community and to during the lockdown period as well, give you a little bit of physics, give you a little bit of a sense of what we're getting up to. The good news is that we are back in our research laboratories at Swansea. Despite all the problems, we're managing to continue in the important science that we do. So the title of this webinar is A Sunny Energy Future and Solar Powered Sheep. Our research group, as James said, is the Sustainable Advanced Materials Group, or SAM for short. And you can find our resources and our knowledge sharing portal at this little link here, Advanced Matter Swansea. And also, of course, you can find information about the General Physics Department research and teaching agenda at this link here as well. Okay, so without further ado, let's continue. And let's start at the beginning. So the people that are contributing to this particular little webinar, obviously James has given you an introduction. Some of our scientists, Dr. Wheatley and Greg Burwell, are at our department in Swansea and our laboratories, and I'd like to thank them up front. And this whole thing was stimulated by an interaction with this particular sheep here called Dolly that we'll hear about in a minute. She's part of the University of Queensland School of Vet Science. It's a very large vet science school. They do a lot of large animal work, and she's basically the star of this show. Okay, so without further ado, let's get on and have a little bit of a look at the content. So what I'm showing you here are some visualizations that NASA has produced. Everybody knows who NASA is. They send men to the moon and missions to Mars. And they have, since about 1970, been collecting global temperature data and other types of data, which shows us how the planet is warming. We'll have a little look at this in a bit more detail in a simulation tool later. But suffice to say, it's a very stark picture that we see in terms of the temperature in 2019, 2020 on the planet. Over the last 20 years, we've had something like 14 of the hottest days and hottest years on record. And here's a little indication. This is the global temperature map from data that was collected from 1880. We've been keeping detailed temperature records, not we, but the meteorological community has been keeping very detailed temperature maps for over 100 years now. And I'll show you a little bit later, but this particular map shows an approximately plus 1.5 to 2% degree increase over the 1880 baseline. So that's a considerable increase in the base temperature of the globe over 120 years, which we'll have a little look at. So that's the starting point for this. There's absolutely no doubt now in any scientific mind that the globe is warming and that we are heading definitely towards a plus 2 degrees C increase on the average global temperature. So here's the content of the webinar based upon that little setup. First, I'm going to talk about some of the earliest thinking on global hothouse or global greenhouse warming by a very, very famous scientist called Svante Arrhenius, who was a physical chemist back in the 1800s. And he had a very simple model for predicting how the global temperature would change based upon changes of so-called greenhouse gases in the atmosphere and the way that the radiation of the planet was reflected or absorbed. And we'll have a look at NASA's climate change machine and climate models based upon some of that very simple understanding. I then want to talk about the situation locally in the United Kingdom, and there's a fascinating web-based resource called GridWatch UK, where we can look at the demand and the supply in the United Kingdom electricity grid. When the sun shines indeed and when the wind blows or not. In Cardiff today it's very windy. I can hear the wind blowing outside my window, but it's not very sunny, and so of course that presents a particular problem if you're trying to generate electricity from sunshine at the moment. Then we'll go and do a little bit more in-depth look at solar energy, and particularly we'll have a look at the two basic types of solar energy, which is photovoltaics and solar thermal energy conversion. And then also another tool that I very much like called Renewable Ninjas, which looks at how one deploys and the resources that one has for renewable energy generation across the globe. And we'll be able to go to various places around the globe and see what potential those places have for generating solar or wind power, for example. So if you want to think about a place you'd like to go to see if it's any good for solar energy or wind energy, think about it now, and then you can make some suggestions on the question function. That's when James will come back with a bit of a quiz. We would have dealt with quite a lot of basic global warming science and quite a lot of energy science by that time, so you should be quite well disposed to have a crack at the quiz. From there we'll go to our labs, and with a bit of luck we'll be able to see some of our scientists making and testing solar cells in the lab. And then finally, if we've got time, we'll have a look at another little tool from the University of Sheffield. Their so-called solar PV predictor tool, and you can basically input your postcode into that tool, and it'll tell you exactly how much solar energy, if you put a photovoltaic system on your roof, it will produce over a year. So that's kind of fun. We can pop our postcodes in and we can see whose house potentially can generate the most solar power. And finally, we'll have a little question and answer and a wrap up, and I will be at the end be providing you a list of resources that I've used to put this webinar together. Okay, so without further ado, let's have a little look at the greenhouse effect, or the so-called hothouse effect, as Arrhenius had called it. Well, I think this is pretty much well known now in science and in fact amongst the more general populace, that the way that the Earth's surface reflects and absorbs radiation is dependent upon the composition of the atmosphere. And there are certain gases in the atmosphere, such as methane, carbon dioxide, even water vapor, which tend to absorb solar radiation and reflected radiation and reflect it back onto the Earth's surface, which is responsible for the global warming. So we can step through this greenhouse gas effect very simply. Obviously, we've got the sun, which is shining radiation upon us. That radiation is multi-spectrum radiation. Of course, the visible light and the infrared radiation is what we're really interested in here. So some of that solar radiation anyway is reflected by the atmosphere of the Earth. And quite a bit of it, including most of the visible portion, is transmitted through the atmosphere and hits the Earth's surface. Some of that radiation is absorbed, and again, some of that is re-reflected back into the atmosphere. Now, in a general sense, the Earth is, if you like, at equilibrium with itself and the sun, and generally speaking, this release and this reflection of radiation keeps the Earth's temperature, surface temperature, within a fairly narrow band of degrees centigrade. But over the last 200 years, we've been pumping all sorts of other gases like methane and carbon dioxide into the atmosphere. And if you like, that balance has been disturbed. And in fact, some of these gases, like carbon dioxide, which I suppose is the best known of the greenhouse gases, these gases, they can reabsorb the radiation and then re-emit it in all sorts of directions, some of it back into space, but some of it back down to the Earth's surface. And it's that re-emission back down to the Earth's surface which causes the problem. Now, a very famous Swedish scientist, Svante Arrhenius, I'm showing his picture here, back in the 1800s actually, and he did win in fact the Nobel Prize for Chemistry in 1903, realized that this balance, this careful balance of the way that radiation was reflected and absorbed, the so-called flux balance, was changed, was perturbed by the difference concentration of gases. So he came up with this very, very simple little one-line equation. And this equation says that the change in this flux of radiation, he called it radiative forcing. The change in this net flux of radiation was essentially proportional to the log of the concentration of a gas at some fixed time, C0, and the concentration of gas at some time later, if it either increased or decreased. So this was his first prediction of how this radiative forcing, this change in the flux of radiation coming from and to the Earth, was changed by the relative concentration of these gases. Now you can relate this delta F, this radiative forcing, to a change in global temperature, an average change in temperature. And it turns out that this little equation, delta T, is approximately equal to this constant here, times the total amount of radiative forcing that you see from all of the gases. So it's an arithmetic mean of all of the gases, carbon dioxide, methane, etc., allows us to relatively accurately predict the temperature change caused by a certain amount of global warming. So for example, I've done a quick calculation here for you. So the radiative forcing caused by CO2 in changing its concentration from 185 parts per million to 265 parts per million is about 1.9 watts per meter squared. And you could quite easily plug this delta F then into this little delta T equation and see what the global temperature change is. So that, in a simple essence, is global warming. It gets a little bit more complicated than that. And the reason it gets a little bit more complicated than that is because of things like the so-called albedo effect. Basically, the albedo effect is the difference in reflection from the different parts of the Earth's surface. So it might not surprise you to know that ice has a quite high albedo, which is the ratio of the diffusely reflected radiation to the incident solar flux. However, water has a quite low albedo, so do parts of the Earth's surface, soil and sand. Dark soil, for example, has a very low albedo. That means it absorbs quite a lot of radiation. So you can see that this has significant implications, because this albedo effect has a cooling effect on the Earth. If you're reflecting more and more of the radiation, then not so much of it gets absorbed. So as we lose the ice caps and as we lose the effect of the glaciers, the overall albedo of the Earth is going down. That is to say that we absorb more of the radiation in the Earth, and therefore we start to see a runaway effect with respect to this global warming. What is the highest greenhouse impact of all gases? Well, there's a question of this in the quiz, so I won't give you the answer. But traditionally, we think of carbon dioxide as being the sort of mean guy in the global warming spectrum. But actually, other gases, for example, like methane, which is produced in quite large amounts from agricultural emissions, has actually got a very high greenhouse gas coefficient, and so has a larger effect for relatively smaller amounts of it. So that's the thing you've got to think about here in terms of the greenhouse impact. So there's a question on that, so maybe you want to do a little ferreting around on the web before we get to the quiz, but there's definitely a question on that, okay? So think about that one. So it's really not just as simple as this greenhouse gas delta F equation that Arrhenius gave us, but it's a constantly changing dynamic as the albedo of the Earth is changing, as the relative concentrations of these different gases is changing, which is why it's a very, very difficult thing to measure. Arrhenius recognized that, and he also recognized that he didn't have the sort of computational power to be able to deal with this back in the 1800s. But of course, now we have massive mainframe supercomputers. In fact, your laptop can do these calculations, and we have very sophisticated climate models, which are allowing us to make some quite startling predictions about what the future looks like. This graph here plots the year from 1860 forward and the relative temperature change compared to 1850 to 1900 average, okay? And it was published by the IPCC in their latest report. You can find it online. This is free for everybody to have a look at. And what we're plotting here in the lighter colored yellow is the measured temperature change, which we assign to human activity. The total externally forced temperature change, which is kind of orange. And then some of the climate models that have been developed, the so-called CMIP5 models, which are sort of averaging of many, many models that the scientists produce. And you can see that these climate models now historically and going forward into the future seem to be quite accurate in predicting what we think the global temperature is going to be. So the near-term projection past 2019 forward, 2020 forward, is that we are likely to see towards something like a 1.5 degree average increase in temperature out to about 2030. And that's why you're starting to hear people talk about this tipping point of when we get near 2 degrees, that things are going to start to get very difficult to recover. An interesting feature of this is the pink area here, the so-called Holocene temperature range. So this is the kind of, if you like, the modern temperature range post the last ice age that the world has been operating under. So it's sort of been fluctuating between plus or minus 0.8 or so of a degree. And so we're now definitely outside the average Holocene temperature range. So that's the prediction of the IPCC as late as 2019. So what we're going to do now is we're going to have a little look at this in a bit more detail by using an interactive tool that NASA have developed over the last couple of years. It's a combination of their advanced modeling tool and historical records of what the temperature and the sea level and in fact the carbon dioxide in the atmosphere has been doing. So I'll go to my web interface now. I'll stop sharing and reshare. So we're now sharing onto Google, and we'll have a little look at the climate time machine. So this is the climate time machine from NASA. So the first thing I think we want to do, you can have a little look at the sea ice and the sea level rises yourself, but I think the most startling one is the global temperature. So what we're doing now is we're loading up the global temperature data from 1884 forwards, roughly 1880. And if I start the climate simulation, data simulation, we'll just to note that down here in the blue, so the blue areas are roughly -4 degrees relative to the global average at that time. And of course, the red up here is the +4. So keep an eye on the way that these colors change over the globe. And I'll also ask you to keep an eye on the distribution of this temperature, where it gets hotter, where it gets colder. And there's some quite interesting things that we don't quite know how to explain yet, but see if you can spot what's going on. So here we go. We're stepping through now the global temperature from 1890. So here we go. We're going to come into the 20th century here now. Things are pretty static, generally speaking, over the globe. There are hot spots and there are cold spots, as one would imagine. But now we're really beginning to enter what you might call the industrialization era now, where the world is truly industrializing after the First World War. And we can begin to see quite large temperature changes through to the Second World War, after the Second World War, and the next phase of industrialization as the world recovered from the Second World War. And something interesting going on, I think, at the North Pole, which we don't quite have an answer for yet, but there seems to be some real changes of temperature up there. The 70s were relatively cool, 79, 80, but 80 was really beginning to start to kick in now, where the carbon dioxide levels were beginning to increase across the globe, and particularly across the permafrost areas Northeast Asia, some big problems beginning to occur. And by the time we're coming through into the late 2000s, where we've seen the industrialization of large nations like India and China, we're at a situation now where some parts of the globe are +4 degrees relative to that base climate back in 1884. So that is a manifestation of climate change, absolutely and real. That data is unequivocal. Let's have a look at the relative changes of carbon dioxide over that time. We don't have carbon dioxide data going back more than about 4 decades. So this is plotting from 2000 on, when we begin to see some real big changes in the carbon dioxide. I'll point to the scale here. This is 365 parts per million. Back in the 1800s, we were probably at something like 250. Up here, we're at 425 parts per million, which is currently where we sit in the sort of late 2019, 2020 period. So we can begin to see carbon dioxide beginning to build at about 390 parts per million in various parts of the globe throughout the mid-2000s. Starting to grow ever larger then, 2010, and now we're beginning to see the first 300 or 400 parts per million emerging again at the poles, and we don't quite understand why that carbon dioxide seems to be building hard up at the poles, but it's likely that is also related to, of course, the way that the temperature is changing at the globe. And again, those large carbon dioxide concentrations over the permafrost regions in Mongolia and the steppes of Russia, which are very dangerous indeed, and again, delivering more carbon dioxide as the permafrost melts. Okay, so we get through now to near present day, and you can see now that we are globally at about 400-ish parts per million, with some areas now beginning to show near 300 parts per million, 400 parts per million, and finally up to the current status where some places on the planet have got 420 parts per million. Okay. Anyway, have a little play with that tool. It's a really cool tool. It's free on the NASA website. Okay, so back to our webinar. So there we've seen some climate models, and now I just want to do a little bit of basic physics for you, because from now on in, what we're going to start talking about is energy. And the reason we're going to start talking about energy is because over the past 200 years, and in fact, as far back as humankind has been on the planet, the first things that we used to use to generate energy, to generate heat, and to generate light, of course, is fire. And that is, fire is the burning of fossil fuels in the form of wood or other combustible materials. So for as long as humanity's been on the planet, we have been burning carbon-based material to create energy. And this is generally still what we do to produce energy, such as transport energy to go in our cars with diesel and petrol. And we burn fossil fuels such as gas and coal to generate our electricity. So we're still burning fossil fuels, we're still burning carbon-based materials. And so the relationship between how much energy and the power of a system and how much power we can generate from a particular form of energy generation is a very simple thing. Recall from your basic physics in GCSE or A level that the power of a system is the rate of doing work, and we measure power in watts, or in fact joules per second, which is energy per unit time. For electrical power, which is what we're going to focus on now, that power is the voltage that we drop across any particular component delivered by a power source times the current that flows through that component. So it's a very simple equation. The power of an electrical system is the voltage times the current. And energy, which is of course related to power in terms of the energy per unit second, is in fact the power times the amount of time that we deliver that energy over. And so E equals P times the time that the power is delivered over gives us a measure of the energy. And in fact, that's a basic description in the electricity sector. And the funny thing is that we talk about huge units when we talk about the amount of power or the amount of energy that the globe requires. And so we have to go into exponent language. And just to remind you, 1 kilowatt is 1,000 watts, or an exponent 10 to the 3 watts, and 1 terawatt, for example, is 1,000 gigawatts. So I'll be talking about kilowatts, megawatts, and gigawatts rather than watts here, because as I say, we need a lot of energy to drive this planet. So as a simple example, the electrical energy and power, if a power station generates 500 megawatts of power on average, that means to say it has a capacity of delivering 500 megawatts, and it delivers that 500 megawatts for 1 hour, then it generates 500 megawatt hours of electrical energy. So often in the electricity industry, you'll hear people talking about megawatt hours. And in fact, when your electricity bill turns up and everybody pays it, you'll be paying for kilowatt hours, that is to say in this regime. So kilowatt hours of electricity is what you pay for when your electricity bill turns up. So there's some basic power and energy physics. Remember that power in an electrical system is the voltage times the current. Remember that energy is the power times the time over which it's delivered over. And so now we go to some big numbers. This is some data from a very trusted source called Our World in Data. And you can look this up, it's freely available online. And this is the amount of electrical energy that the world needs per annum in 2018, actually, this data is from. And you can see these are huge numbers. The world requires 140,000 terawatt hours of electrical energy to run its business on an annual basis. The other interesting thing about this graph is the relative portion of where we get that energy from. Traditional biofuels, funnily enough, has a sort of base load, and this base load is associated with things like burning peat and burning kerosene for fuel and cooking in the third world. So there's still a significant amount of biofuels, traditional biofuels you might call them, that are burned in the third world. Coal still makes up a quite significant portion, about a third, I guess, of our total electricity generation. In some parts of the world, crude oil, South America, for example, crude oil is burned still as a means to generate electrical energy. And natural gas is more and more being seen as a transition fuel, that is to say, a fuel which has lower greenhouse gas emissions per unit of electricity it produces, but still, of course, is a non-renewable source that we have to get out of the ground and burn and produces carbon dioxide. And then we have the so-called clean powers. Nuclear power sitting in here, still a relatively small proportion of the world's energy. Solar and wind growing, and hydropower as well, growing quite large. So this is the kind of global view, if you like, circa 2018. What does it look like in the United Kingdom? So in the UK, it's a bit of a different story, actually. And this is data from 2019 that was published by the Department for Business, Energy and Industrial Strategy. So I guess they should know what they're talking about. And the government is saying that roughly 300 terawatt hours compared to 140,000 terawatt hours, if you remember the global energy use. 294, roughly 300 terawatt hours was the electricity that we required in 2019. And this is rather interesting. So this is the if you like, the breakdown of the sources that we take our electricity from, and we can see a very stark thing happening with the amount of coal that the UK is burning. In fact, percentage change on a year earlier, that is relative to 2018, we've burned 59% less coal to generate our electricity than we did the year before. Our nuclear power is down a little bit, but that's going to be creeping up again as we build new power stations. And the big mover, of course, was renewables, as more wind and solar power came online, and we started actually to burn a little more gas as well as a slightly cleaner alternative. The good thing is as well that our energy consumption is down, electricity energy consumption is down by about 3%, so that's good news. Okay. And before we go and have a little look more at the detail of that, using this thing called GridWatch, which is an excellent tool, which shows you how the UK grid is performing, I just want to make a few comments about so-called capacity factor. This is a very, very important concept in electricity generation. The capacity factor is essentially the percentage of time on average that any electricity generating system produces its rated power. So for example, if I had a 500 megawatt capacity nuclear power station, and it was able to produce 500 megawatts for 24 hours a day, 365 days a year, it would have a capacity factor of 100%. So in principle, when you burn fuel, as long as you have enough fuel continuous supply, like gas or coal, or indeed nuclear, then it should have capacity factors approaching 100% if you're running it 100% of the time at its rated capacity. In principle, you can also run biomass, whether it be natural biomass or be fossil fuel non-renewable biomass at 100%, as long as you've got enough of the resource. But renewables are very different in that, for example, wind and solar are not always available 100% of the time. So renewables are resource dependent. And this is a big paradigm shift for the electricity sector, because that fact that it's resource dependent means that we have so-called intermittency. That is to say, there are times during the day or the night when you have no solar and you have no wind. Clearly, you don't have any solar during the night. So typically, solar can produce in the best and sunniest places in the world, for example, North Africa or Australia, capacity factors of about 25 to 30% as a very maximum. That is to say, without storage, because clearly if you could store some of the electricity produced from solar power during the daytime hours and then discharge it to the night, then we'd have higher capacity factors for the system as a whole. And it's the same for wind. Wind, particularly in places like the United Kingdom, has got higher capacity factors, especially if it's offshore wind. And generally, we see capacity factors of about 40% maximum for wind systems in this part of the world. But as I say, in both cases, where you have intermittency, and if you can create storage with, for example, batteries, then it is possible at some cost to produce 100% capacity factors with renewables. Now, let's have a little look at what's going on the United Kingdom grid as we speak. And this is a little tool that we, that's called GridWatch. And this is a tool that you can use for free. It's a great little resource. And what it's showing here is the United Kingdom national grid. And it's a fascinating little resource. It shows at the moment, for example, that the peak demand in the United Kingdom right now at 14:03 on Monday is 30.6 gigawatts. And that actually gives you the frequency as well of the alternating current that's flowing through the grid. Generally speaking, electricity generators run at about 50 hertz, and that's to do with the turbines on the power stations. But at the moment, we're using just a tad over 30 gigawatt peak power. About 40% of that at this very moment in time is coming from renewables. So that should make you smile. And I want you to also think about what most of that renewables is going to be coming from at this moment in time, considering it's a pretty cloudy day. We're not playing any cricket in Old Trafford, and the wind is blowing very hard. So at the moment, our nuclear power stations are producing about 5 gigawatts, which is about 17%. And these things here are called closed cycle gas turbines. So these are basically gas power stations, gas-fired power stations with turbines creating the electricity off the back of them. The other thing I want you to notice that we're burning zero coal at this moment in time in the United Kingdom. All right, and there we are. The wind is blowing, so we're producing 25% of that 40% total of renewables is coming from wind. With about 8% of it coming from solar. So it's a pretty overcast day, but it must be some places in the United Kingdom where the sun is shining. Okay. The remaining renewables is coming from hydro. The other interesting thing is that this shows the so-called interconnects both to France, to the Netherlands, and to Ireland. And you can see at the moment that we are taking about 3% of our electricity from France, about 3% from the Netherlands. So we are a net importer at the moment from those two countries. Sometimes we export to them, so we sell electricity back to the French and the Dutch and the Irish, but today they're selling a little bit of electricity to us, probably because of the weather at the moment in the United Kingdom. And these little graphs here are sort of the averages of what's happening in the UK at the moment. They're 10-minute averages, and the different colors show you the different amounts of electricity being generated from source. And there's also a whole bunch of historical data that you can see that's also provided. You can download this data and you can do analysis for yourselves and see, you know, times when we're generating a lot of solar power, times when we're generating a lot of wind power, and times when we're relying on our gas-fired power generators as well. Okay, so that's the status of the UK grid at this moment at 14:06 on the 27th of the 7th, 2020. Right, so back to our PowerPoints. So we know a little bit about power now. And so next, let's have a look at a very, very specific power source, shall we? A power source that's been sitting up in the sky looking at us for a very long time indeed, and that is the sun. And what I'm showing here are a few key statistics of our sun. It's a fairly big entity, about 700,000 kilometers in radius. And the thing that staggers me are some, even though we regard it as being a big ball of gas, the size and the mass of it is quite staggering. And for example, the escape velocity, if you wanted to leave the sun, is 55 times the Earth, and the surface gravity is about 28 times the Earth. So it's a big mass within our galaxy. But this is the interesting figure. Its luminosity, or the amount of luminous power it gives out, the amount of light power it gives out, is roughly 4 times 10 to the 26 watts. So that's 4 with 26 zeros stuck after it, which is a huge amount of light power that's coming out of it. Now, of course, not all of that reaches the Earth. A certain fraction of it reaches the Earth, and the spectral characteristics, the color of that light reaches the Earth. Well, we know there's a lot of it in the visible, and what I'm showing here is the so-called spectral irradiance. That's the power, if you like, per meter squared per nanometer, against the color in wavelength in nanometers. As I say, the visible's down here, the near infrared is out here, and then we go into the mid infrared. And at the top of the atmosphere, which is this yellow band, that's the essentially the power that reaches the luminous power that reaches the outer atmosphere. And then as the light comes through our atmosphere, some of it is absorbed by molecules such as water and oxygen, carbon dioxide, methane, etc. And that gets us back then to the discussion we had about greenhouse gases. So it's attenuated considerably, so less radiation reaches the Earth's surface than at the top of the atmosphere. And this red is the so-called AM 1.5 or air mass 1.5 spectral density, which is essentially the resource that we have to play with if we want to make solar power from terrestrial solar power systems. Of course, we could just launch a solar plant into space, couldn't we? And in fact, the space stations and the shuttle all had very sophisticated and very efficient solar power generating systems on them to generate electricity while they were orbiting the planet or going to the moon. And so the resource at the Earth's surface is a bit different, as I've just showed you. And so we call it air mass 1.5, and it's the standard spectral resource that we have hitting the Earth's surface. So we know there's still a lot of visible light in there. About 45% of it is visible. This ultraviolet is the stuff that gives us suntan and sunburn, and in fact skin cancer if we get too much of it. And this infrared component is the hot component. This is the stuff that will make you very warm. And we can't see this. The human eye cuts off at round about here. So we see red, but not much past that, okay? So that's the AM 1.5 resource that we've got on the Earth's surface. And this is a place on the Earth's surface which has more of this air mass 1.5 purely than any other place on the planet. And this is in South America. And that chap there is me. About 5 or 6 years ago, and I was in Chile, which is where this is. This is the Atacama Desert, up in the high antiplasta of the Chilean Atacama Desert. This is the Andes, and this is the South Pacific. And what we're looking at here is probably a place around about there. And this is one of the driest, if not the driest place on the planet. On average, they get about 1 millimeter of rainfall a year. And we were up there working between the Australian and Chilean governments, surveying for the best place to build a solar plant. And the Chileans have got a very significant plan. They want to cover the Atacama Desert with solar power. and then they want to build a direct current high voltage DC link all the way to Central America and South America, Argentina and Brazil. And they have a plan to supply South America with 30% of its power from the Atacama Desert by 2030. I think it's a rather ambitious plan, but if you think about the resource they've got up there, then it's probably quite a sensible way to provide green power and to use that particular solar resource. So it's a heck of a place up in the Atacama Desert, wonderful place for solar power, uniform AM 1.5, 365 days a year. On average, I think capacity factors of about 27%, and we can maybe have a look at that when we go through our next tool. So that's the Atacama Desert. And we measure this resource that reaches the Earth's surface by a thing called insolation. And the insolation is the energy per unit area per unit time. And we can see that on this map of the planet, the areas that are very red produce insolations of roughly 1,000 to 1,400 kilowatt hours per meter squared per annum. And the ones with very low insolation, that is to say low solar resource, like for example the United Kingdom, are about a fifth of that. And I used to live in Brisbane, which is round about there in southeast Queensland, and we built solar power plants all the way along on the inland roads that was west of Brisbane. Extremely good insulation, you can see there, between 1,000 and 1,200 kilowatts per meter squared per annum. And Britain, as I say, not terribly good insulation. Neither is Germany, that has a considerable portion of solar power plants. Here's California, here's Southern California, excellent resource in Southern California, particularly in places like the Mojave Desert. And here are our friends in the Atacama Desert in Chile, Sub-Saharan Africa and South Africa, again, not surprising, very large amounts of solar resource. And of course, in the Middle East, also large amounts of solar resource. So that is the global picture, if you like, of global insolation. And now we're going to have a little look at a tool called Renewable Ninja. And I asked you at the introduction of the talk, of the webinar, to have a little think about where you'd like to go to see how good the solar or indeed the wind resource is. And I can maybe while I show you the Renewables Ninja, maybe James, you can have a look to see if anybody has suggested any places that we might want to stop along the way to see if we've okay. So here we are on Renewable Ninjas. We've got the whole planet before us. We can look at the solar resource by specifying a few things. We can look at the wind resource by specifying a few system parameters. So I tell you what, let's start off, shall we? Let's start off in the United Kingdom. Let's start off in Wales, yeah? And let's start off in Cardiff, because that's where I am at the moment. And I'll place my blob just on the top of Cardiff, because that's approximately where I am at the moment. We're at latitude 51.5 degrees and longitude -3, so we're just west of zero line. And we now need to specify a few solar parameters. So if you want to play with this on your own, that's fine. But what we're going to do is we're going to look at the historical weather data from 2019. Of course, we need some historical weather data. I'm going to specify a typical solar system that you might put on your roof, which is about 5 kilowatts. So those of you who've got photovoltaic panels on your roof are about 5 kilowatts probably. And there's a great skill in aligning your solar panels to get the most radiation and therefore produce the most electricity. And it turns out it's a really good idea to incline or to tilt your solar panels at your latitude, because that gives you the most sort of direct facing to the sun over the course of the year. So I'm just going to orientate my solar panel at 52 degrees. And this thing here is called the azimuth. And it basically is whether it points northward to the pole or southward to the pole. And in the northern hemisphere, you get most solar radiation when you point things to the south. And that's why, for example, when you buy a house in the United Kingdom, you always want a south-facing garden so that you can get most radiation. If you live in Australia, it won't be surprising to know that you would like a north-facing garden because that's where you get most radiation. And so a solar panel system in Australia will point northwards. So I've got all the parameters in there, a 5 kilowatt little system sitting on a roof in Cardiff with a tilt of 52 degrees. That's the angle on the roof, pointing due south so we can get most radiation. And I can run that little simulation now. Takes a couple of seconds to do. It's downloading the weather data. And this is the output as a function of time from January 2019 to the end of 2019 in December. And you can see it's got kind of this roughly sort of bell shape to it, this circular curve to it. It's no surprise that you get most electricity. This is the amount of electrical energy produced, okay? And it doesn't surprise you that most of it is produced in the summer months between April and October, so in spring, summer and early autumn. And then when it's pretty dreary in December, we of course don't get much solar power produced. And here we can see a calculation of the so-called mean capacity factor. This is what I defined for you in a few slides ago, which is the amount of time that, for example, this particular system would generate 5 kilowatt output as a function of time. And you can see that the capacity factors peaks at about sort of 20-ish% during the summer months and falls as low as 5%, 4.3% in December. So it's not generating a lot of electricity at all in December. So do we have any suggestions? Do we have any suggestions, James, for anywhere to go?
Yes, we do. Hi, Paul. So we have a couple of suggestions. First one is Seoul in South Korea.
Oh, Seoul in South Korea. Okay, let me see if I can find Seoul in South Korea. Okay, best thing to do is Seoul in South Korea. Okay, let's have a little go, shall we? Okay, so there we go. We got you. Right, Seoul in South Korea. All right, so the same system. Now, of course, I should change the latitude and the tilt to 37 degrees. Otherwise, that would be a bit unfair to Seoul, wouldn't it? We'll use the same data set. So Seoul, South Korea. And remember the capacity factor for Cardiff, right? 12.9% average capacity factor of the year. Now, we're going to continue to orientate towards the poles. And let's run it. Let's see what we get. Anybody's guess as to whether it's more or less. And the mean capacity factor is 17.4. And we could probably have predicted that, of course, because Seoul is 37 degrees latitude, so it's nearer the equator than Cardiff is, which is 51%. So you would naturally, being further south, have a heavier insolation. And if we looked at the insolation map, we'd probably see that. That interestingly, and I've never modeled Seoul before, you can see that the capacity factors in Seoul peak in May-ish. So we're still in the Northern Hemisphere, okay? So we still have that kind of peak in the May, June, July. But it probably turns out that the rainfall patterns and the cloud patterns also influence when the peak capacity factor is, because of course it doesn't matter if it's very warm, if it's very cloudy and you're having monsoon rains, for example, or heavy rainfall, precipitative rainfall, then you're going to shadow your solar system and you're going to have lower capacity factors. So those things are taken into account in the modeling as well, by virtue of the fact that there's real insolation data as a function of time in the model. Have we got any other suggestions?
Yeah, we've got quite a few coming through, actually. Oh, yeah. Let's go with Havana in Cuba.
Havana. Oh, this is exotic. I like this. There we go. Let's have a little look at Havana. Let's go this way, shall we? Testing my geography now, you guys, aren't you? Okay, so here we go. Let's go to Havana. Never been to Havana, always wanted to go there. So let's go there now, shall we? There you go. We're in Havana. And Havana is 23 degrees. So Havana's getting quite close to the equator now. So this is 23 degrees. So let's pop 23. So we had Seoul coming in at 17. We had poor old Cardiff coming in at 12.9. And we should, of course, now be able to predict what Havana's going to do. Although it is quite close to the equator there in the subtropics. And here we have a capacity factor of nearly 19%, 18.6%. So Havana's the winner so far, 0.6% over Seoul. And again, you can see this really interesting, dynamic in terms of the capacity factors. And when it peaks in capacity factor, it kind of peaks somewhere in the spring, associated, I guess, with the precipitation, the rainfall dynamics. And if the person that asked me about Havana actually has been to Havana, then they can probably give us some advice on this. Personally, I've never been there, so I wouldn't know. One more then, just one more, James.
Okay, well, okay, so I thought further south would be good. We've got Santiago in Chile.
Ah, Santiago, wonderful. I've actually been to Santiago in Chile.
And then we've got one that's a bit closer to home. Maybe we finish on that.
All right, maybe we'll do that. Santiago, Chile. Santiago, lovely, lovely city, wonderful city. By the way, Antofagasta is where I showed you that. That image. So let's go Santiago. Yeah, fantastic solar resource there. It's minus 34, and so this time we're going to be facing the panels due north, right? In order to get the maximum capacity. So again, we're going to do a 5 kilowatt system. I think Santiago is going to give us a relatively high capacity factor. And there we are, 22.5%. There you go. There's the Chile effect.
Okay.
That's a corker. And again, we're in the southern hemisphere now. And look at this. Now this is perfect. This is basically mapping the passage of the sun across the southern hemisphere in the absence. Santiago is actually relatively dry, of course, being on the western side of the Andes. And so we've got the perfect textbook, almost cloud-free type of response. So that's a fantastic one. Whoever suggested that one really knew what they were talking about. And nice and uniform as a function of time over the year as well. So that's a good place to do it. Okay, one last one then.
Okay, so we won't be able to do several of these, I'm afraid. But how about one closer to home, Lincolnshire?
Lincolnshire.
North Lincolnshire.
Right. I think Lincolnshire is a good place to do this, actually. It's a corking place to do it. Right, so Lincolnshire. Of course, the east of England, the east of England tends to have higher. So we can see. So I can find Lincoln. Tends to have higher degrees of sunshine than most of other parts of Britain. Okay, so there we go. Here's Lincoln. Yeah. So let's get Lincoln, shall we? Right. Everybody good? 53 degrees, so it's slightly further north than Cardiff. So all being equal, of course, it should have a lower capacity factor. But Lincoln is definitely drier than Cardiff, and so I think what we might find is a marginally increased capacity factor relative to the 12.9. Was Cardiff 12.9, wasn't it?
I think so.
Okay, so let's see where we go. 12.1. I was wrong. So Cardiff, by virtue of its slightly lower latitude, slightly closer to the equator, a little bit higher insolation, and Lincoln has a nice double bump look in its capacity factor. So maybe it's a little bit wetter. It was maybe a little bit wetter in June last year than in other places in the United Kingdom. Okay, so that was good fun. Please have a little look at Renewables Ninja. What you will have to do, if you want to use it for more than 15-20 minutes, you will have to register online. It doesn't cost you anything. You can register with your school, and it's a fantastic resource. Okay, so let's go back to our main PowerPoint slides. Okay, so we're in the Atacama Desert. And now, just to give me a little bit of a rest from my throat, James is going to take over now and is going to open the poll so that you can test yourself to see if you've been listening over the last 50 minutes or so, and answer some questions. So I'll just hand over. I'll shut up now and I'll hand over to James.
Okay, thank you very much, Paul. So let's just. Okay, so we have a short quiz. Can you stop screen sharing maybe, Paul? There we are. Okay, so I'm going to open a poll. Hopefully this will appear somehow in your Zoom session. So what I thought I'd do is, to save this just being a dry exercise you do on your own, I'd talk about the questions a little bit. So there's only 8 of them. Hopefully it won't take us too long. I think this will probably take us about 5 minutes. Question 1. So if you can't see these, please do scream at me on the chat so that I know, but I'm going to assume you can see them. The first question is, which of the following gases in the Earth's atmosphere make the largest contribution to the greenhouse effect? So this is an interesting one. Paul mentioned several gases early on. I think he mentioned exactly the set that we have there. So water vapor, ozone, methane, and carbon dioxide. So he's been talking about carbon dioxide a lot. Is that the largest contribution? Possibly, maybe. It's the most important human one, but is it the largest? Okay. Question 2 is a little further away from Earth, a little further away from home. Where in the solar system can we find an example of a runaway greenhouse effect? So something where the greenhouse effect has drastically changed the planet. So the options are Venus, Mars, Jupiter, and Titan. There are other moons of the gas giants that we could have chosen. Titan is an interesting one. Okay. So question 3. The UK Climate Change Act of 2019 commits the UK to achieve zero net emissions of greenhouse gases by when? So we'd like that to be last year, please, or sooner. But when will it be? When are we legally obliged to achieve this? And then is it 2025, 2030, 2040, or 2050? So of course, the data in the slides that Paul showed should be very concerning. Fortunately, there are things that we can do. Okay, question 4. Question 4 is, I'll read it out first. I like this style of question. So a 40-watt light bulb, which we don't use anymore for climate change reasons, but traditionally light bulbs were that sort of power consumption. A 40-watt light bulb on continuously uses a power of about 1 kilowatt hour per day. What is the approximate average power consumption of a person in the UK, taking all demands for everything, heating, transport, lighting, cooking, and gadgets into account? So this is a very physicist sort of question. There's a famous one, how many piano tuners are there in Chicago? These sorts of things, you don't have enough information to get a precise answer, but you can use the partial information you have to get a half decent answer. So this sort of question is very much thinking like a physicist. Okay, question 5. This is about nuclear power plants. So the Hinkley Point C nuclear power plant, which is currently under construction, will generate 3.2 gigawatts. So this is a lot of energy, a lot of power. So you can maybe, as a physicist, ballpark think how many we would need. How many such plants will be needed to supply a quarter of the UK's current energy needs? Would we need 3 of these at 3.2 gigawatts each, or 20, or 100, or perhaps we'd need 1,000 of them? Okay. Question 6. Offshore wind farms are capable of generating 3 watts per square meter. What area of sea, therefore, will be needed to supply a quarter of the UK's current energy needs? So these sorts of questions are fantastic because you just think, well, how much wind energy is there? How much can we extract? All right, then you just divide one by the other and get an area. Again, very much a physicist sort of question. There is a book, a fantastic free online book, which I'll link after this quiz, which guides you through how to think about these sorts of problems and how not to get distracted by the details when you're trying to think about the large scale problems. Okay, question 7, the second to last question. So the Swansea Tidal Lagoon is designed, unfortunately it was designed, this project is now, I believe, officially not going ahead. The Swansea Tidal Lagoon is designed to be the world's first tidal lagoon power plant, delivering power averaged over a day of about 600 megawatts. What fraction of Swansea's energy needs does this represent? So this is very much like the previous couple of questions, one about Hinkley Point and one about the 40-watt light bulb. you're thinking, okay, well, how many people, how much power does everybody use? Divide one by the other and you can get a reasonable answer, even though it's not perfect. So the tidal lagoon, for those who don't know, the idea is that as the tide comes in, and we have a huge tidal range here in Swansea, we've got about 9 meters, which is one of the largest in the world. So a large tidal range, water comes in, you trap it behind a dam, and then you let it out through a turbine. And of course, you can do the reverse. You can let it in through a turbine. So you generate energy as the tide comes in and as the tide goes out. And the idea was to build a great big dam in a sort of a semicircle and trap water behind it. Although this particular project is not going ahead, I believe, there are other ideas, similar ways, perhaps simpler, bigger ways to generate energy from tides. This is saltwater engineering is difficult, but it's a lot of energy and we can extract it with turbines and traditional methods. Okay, last question. Australia has much more solar resource than the UK. No one's going to argue with that. If the capacity factor, which Paul described earlier, if the capacity factor for fixed panel solar photovoltaics in the UK is on average 11%, is the average for Australia for the same solar panels, is it the same, twice as high, 10 times as high, or twice as low? So there's really only one answer there that makes any sort of sense. Okay, so that wasn't 5 minutes, that was 7.5, but we're getting a few answers streaming in. So just give it a couple of minutes for people to settle down and wait until these answers appear to have stabilized. And then I will end the polling and talk through the answers. So I've just posted a link to that Renewables Ninja. So for the people who couldn't do, we didn't get around to. So we had Ecuador, Namibia, Anchorage in Alaska, Santiago in Chile, or we did that one, and southern Portugal, Faro in Portugal. Okay, I think the answers are just about stabilized now. So, I'm now going to end the polling. Okay, so question 1. We have answers. So a quarter of you said carbon dioxide, half of you said methane, and a quarter said water vapor. The correct answer is water vapor. So this is a huge contributor, estimated to provide just over half of the net greenhouse effect on Earth. The important point is that this is not the thing that we are changing lots. We're changing carbon dioxide. So that is the most important effect that humans have had on the atmosphere. Methane, perhaps that was a bit of a red herring. That is important. I think methane is, I don't want to get this wrong. So I think methane is much more important per unit mass, but there's much more carbon dioxide. So Paul mentioned methane by name, so I think that misled some of you. That wasn't intentional. The main learning outcome is that water vapor is surprisingly important for climate change, but carbon dioxide is the thing that we should be affecting. Okay, so next, where in the solar system can we find an example of a runaway greenhouse effect? Over half, 64% of you chose Venus. That is the correct answer. So it's got a very thick carbon dioxide atmosphere and traps incoming heat from the sun, keeps the surface temperature very high, about 470 degrees C. Okay, question 3. So the majority of you picked on the correct answer, is that we are legally obliged to achieve net zero emission by 2050. So this is clearly not soon enough. If we are to achieve something like less than 2 degrees C above pre-industrial levels. This is the legal obligation. As you have seen from the grid watch, we're actually doing rather well in decarbonizing the national grid. And there's a surprisingly large fraction of our energy already comes from renewables, and there's much more going on. So the 40-watt light bulb question. So the answer for this is answer B, about 100 kilowatts per day. So for a proper explanation of this and the way to get these numbers, I refer you to the book I mentioned, which is called Sustainable Energy Without the Hot Air by David Mackay. And I will post a link to that onto the chat. It's available freely online. It's a fantastic introduction to how to think about this subject and getting some sort of clarity on the big scale questions without getting bogged down in the tiny details. We can worry about the details when it's necessary, but to get an overall picture, this book is just superb. So I strongly recommend you have a look at that. As for the Hinkley Point question 5, the answer is B, which 70% of people got there. We would need roughly a nuclear power plant of this size every 150 kilometers along the coastline, which is, well, I think that's far less unreasonable than pumping lots of carbon dioxide into the atmosphere. Fortunately, there's a halfway with lots of diverse range of renewables. Okay, so the offshore wind farms question. Offshore wind farms capable of generating 3 watts per square meter. What area will we need? So this is, the answer is C, which is an area roughly equal to the size of Wales, which is of course where we're broadcasting to you from today. Okay, the tidal lagoon question. The answer is B. It would provide about 1/5 of the energy for Swansea. About 1.5 million kilowatt hours per day, and the Swansea population is 300,000 or thereabouts. Okay, and the final question. Australia has much more solar resource. Is it the same as 11%, twice as high as 11%, 10 times as high as 11%, or twice as low? So it's not the same because we said it's more. It could be twice as high, sounds reasonable. Can't be 10 times as high because that would be 110%. It can't be more than 100%, the way Paul defined it, and it's definitely not lower. So the answer is twice as high, answer B. So with that, I will hand back to Paul, assuming he's here. Hello, Paul.
Good day, James. Thanks for that. I learned some stuff there as well. Thank you.
Okay. Good.
And we'll crack on. Okay. So I would just now want to start in the next part of the webinar and have a little look at a bit more technical detail about what this thing solar power is all about. And specifically, I want to talk about 2 forms of solar power. Generally speaking, we tend to sort of focus our efforts, particularly in the UK, on the photovoltaic side of the equation. We see many houses in the United Kingdom with solar panels on their roofs. There are large solar plants along the M4 corridor near Swindon, for example, and in many other places in the United Kingdom. We see them in farmers' fields, for example. We tend not to build huge big solar plants like you do in North Africa, but we do have, you know, as we saw, a significant portion of solar power generating systems from the photovoltaic effect. But there's another form of solar energy conversion that we don't talk about so much in this country, and that is so-called solar thermal. Now, some of you will be quite familiar with solar thermal. Solar thermal does exactly what it says in the tin. It traps the heat energy of the sun and heats a working fluid to do some work, to drive a gas turbine, to generate steam, or just to heat hot water so you can have a shower. And in many parts of the world, many hot parts of the world, the primary source of hot water at a domestic and indeed an industrial level comes from so-called solar thermal. I had a solar thermal system strapped to my roof in Brisbane, and it produced all the hot water I needed for a family of 4. Okay, for zero cost. So we're going to have a little look at these two forms of solar energy conversion. Let's just have a little look in detail at photovoltaics to start with. Well, the photovoltaic effect, as many of you will know, comes about in semiconducting materials, materials such as silicon, and we'll have a little look at some semiconductors a bit later. The photovoltaic effect we've known for maybe 150 years, and it is the direct conversion of photons of light, to electrons, the stuff of electricity. So it's photon to electron conversion, or photons to volts, as the original pioneers of the field described it as. And photovoltaics can give you power conversion efficiencies of order between about 15% and 40%. Power conversion efficiency is the relative amount of electrical power you get out versus the relative amount of optical power or sun power that you put in. So it's power in over power out. And as we've discussed, the problem with photovoltaic solar power is when the sun suddenly doesn't shine, the photovoltaic effect turns off very quickly indeed. In fact, in all solar data that you can look at, you can see the effect of a cloud moving across the sun in the electrical power. It's that quick. It reacts on a matter of seconds, and that causes this thing that we call intermittency, which is a bit of a problem for the grid because you get these surges of power being produced in the system. Now, looking at solar thermal systems, we have this absorption of the thermal component of the sun's radiation. We generate steam, and you can actually generate steam at very high temperatures by placing the system under pressure. So very large so-called concentrating solar thermal systems can generate superheated steam to drive a steam turbine. We can use the heat directly as hot water, or indeed we can drive a turbine to generate electricity. Now, the interesting thing about solar thermal is it has a much larger kind of time lag. There's this intrinsic sort of thermal lag built into the system, so that if the sun goes away, you suddenly don't get just a turn off of the thermal power, because there's a sort of latency of specific heat capacity in the system. And in fact, the other thing to note about the difference between solar thermal and solar PV is it's much easier to store heat and cold than it is to store electrical energy. We generally store electrical energy in batteries or things like supercapacitors. Pretty much everything on the planet can store heat or cold, right, to varying degrees. So if I was to, try and design a system where I wanted to store some energy, I would probably design a solar thermal system. Anyway, that's the two forms of solar energy, and they are manifest in various parts of the world. These little solar thermal systems, for example, these are sort of heating panels that you can put on people's roofs. This is on the roof of a warehouse, and it generates hot water for the people using the facility. This is a slightly higher, more sophisticated system. It's a parabolic mirror. That's a half sphere of a mirror with a collector going down the middle, which is a pipe containing a working fluid, and the heat energy and the light energy is reflected up onto these pipes to heat them. This is a kind of interesting thing here over on the right hand side of the slide. This is a solar thermal driven air conditioning unit, which is a bit of an oxymoron if you think about it. So this system is used to cool houses and buildings in hot parts of the world via a heat exchanger process, a two-phase heat exchanger process. Very expensive, but a kind of neat way to air condition your house with the sunshine. At the large scale, there are three basic ways of collecting solar thermal radiation. The first is a so-called central receiver, and we'll have a little look at that in more detail in a second, where you have these little things called heliostats, which are mirrors that take the sun's radiation, follow the sun around on a minute-by-minute basis, and shine that radiation up into a big central thermal block. And that can be a block of graphite, or it can be an absorber with a high specific heat capacity working fluid. The other form is so-called parabolic dish. This is a single dish with a receiver at the center of the dish, with the light being focused on the receiver. And this one here is called a trough. You have a linear trough with a pipe down the middle of it, which contains the working fluid. And again, in 2 dimensions, the light is reflected up and absorbed into the pipes. And the largest solar thermal plant in the world is this thing. This is called Ivanpah. And I had a little bit to do with the design and implementation of this when I was younger. But this, at the moment, is the largest solar thermal plant in the world. And it's out in the Mojave Desert. And it was completed in, I think, about 2017. And this produces a considerable portion of the electricity for Southern California. What we have is these heliostats that I talked about in my little schematic, a central receiver tower, and all of these heliostats are reflecting the sun's light into this central receiver. So you can imagine how hot it gets up at that central receiver. And I've got a little video to show you here from CNN, which was made a couple of years ago. If I can find the right window. It's kind of neat little video.
At first glance, it looks like an oasis in the middle of the Mojave Desert. But the Sea of Blue is actually the work of more than 170,000 mirrors, each one reflecting the sun's energy onto one of 3 459-foot towers.
This is the largest concentrated solar thermal project in the world.
The Ivanpah Solar Thermal Plant sits on 3,500 acres of desert, nestled in between the Clark Mountains and Interstate 15, near the California-Nevada border. And it's every bit as large as it's made out to be.
It's actually 3 projects on this site, in total 392 megawatts. The project will eliminate 400,000 tons of carbon emissions. That's like taking 72,500 cars off the road.
NRG says the 392 megawatts equates to enough power for 140,000 homes, or roughly the population of Pasadena, California. Now, the solar panels used at Ivanpah aren't the photovoltaic kind you might see on a rooftop. These panels follow the path of the sun throughout the day and reflect its heat onto steam generators located at the top of the towers.
There are benefits to solar thermal over photovoltaic. I think the most important one is it's less disruptive to the grid, because when you lose sunlight, this project will slowly come offline, where photovoltaics almost immediately come offline.
A big project like Ivanpah comes with a hefty price tag, $2 billion. And it got a sizable assist from the federal government to make it work.
So the way this project was financed, because it's an innovative technology, it would have been very difficult to obtain bank debt. So the project received a $1.6 billion DOE loan guarantee. And if it weren't for that loan guarantee, we wouldn't be standing here today celebrating the Ivanpah project.
While Ivanpah is currently the biggest solar project in terms of energy output, it's not likely to hold that title for long. Mid-American Solar is currently working on a solar plant that will output nearly 1.5 times the 392 megawatts that Ivanpah generates. Jason Sanchez, CNN Money, Ivanpah, California.
Okay, so you can see there that large plants, large solar thermal plants are being built around the world, but they are very small in number. And in fact, the reason that they're quite small in number is exactly what that man was talking about. The cost, the relative cost of building a concentrating solar thermal plant like that is roughly 4 times the equivalent cost of building, for example, the same size gas generating plant. So you can see that the economics of it are still rather difficult. And the American government there has taken a view that this is so important that they need to actually help the funding of it so these things can get built. And the British government and various other governments around the world are also taking that perspective. So that is my favorite solar plant in the world. And it's currently operating at about 390 megawatts, okay, which is a relatively small power plant in global terms, but still a very significant one for solar thermal. And as we discussed a little bit earlier, the way that you can increase the capacity factor of solar power is to use storage. And this is in fact a typical schematic of a solar thermal plant which has got storage. We've got the generating bit here, whether it be a linear reflector or whether it be a tower. Then we've got a storage element, and these storage elements in this case contain some salts which have got very high specific heat capacity, so they can hold the heat for many hours. That can then be be taken in from the solar plant, or it can be released at times where we haven't got any solar power to generate steam, and that steam can then generate electricity via a turbine. So this is a classic sort of power plant, which looks very much like a coal-fired power plant or a gas-fired power plant, except the heat is coming from the solar thermal plant, not burning. And so here's a real image of a solar thermal storage system. There's a cold tank and a hot tank, and the salts, when they become cold or hot, get pumped between the two, and this is how the heat is managed, if you like, to create increased capacity factors. Okay, so let's turn to photovoltaics now, something that probably people are a little bit more familiar with, and this is a silicon solar module. This is a silicon photovoltaic module made out of the crystalline elemental semiconductor silicon, and this is what about 95% of the solar panels in the world are made from. It's a technology which is maybe, I don't know, 40 years mature. And over the 40 years, we've managed to get the efficiency of this technology up to about 25%. That is to say, this power conversion efficiency, the amount of electrical energy power, the amount of electrical power that you can produce versus the amount of light power that goes in. There are other types of semiconductor-based photovoltaics. This one is a so-called thin film semiconductor panel. This silicon panel, for example, the silicon solar cells are about 500 microns thick. That's about 0.5 millimeter. Each of these individual cells is about 0.5 millimeter thick. Whereas this particular thin film solar panel, made from a material called cadmium telluride, is only about 50 microns thick. So maybe 1,000 times thinner than the silicon panel. It uses less semiconductor, therefore, but it's not quite as efficient. It's about 16 to 18% efficient, I think, is the world record at the moment. A little bit of a problem with it in that it's got cadmium involved, and of course, you know, cadmium is quite a toxic material. But suffice to say that this particular material, this particular solar panel technology, has quite a lot of the market share, maybe 4 or 5% of the market share. And then something a little bit more exotic. This is the stuff that NASA sends up onto its satellites. Obviously not with these big towers, but this is made from so-called epitaxial multi-junction compound semiconductors. In fact, 3,5 group materials such as gallium arsenide, gallium arsenide, and materials like that. Highly crystalline, very, very difficult to make. And in fact, some of these materials have got very rare elements like gallium in them. These are very expensive. These things cost a couple of 100 times what a silicon solar panel would, for example, and they're used in very highly specialized applications such as space photovoltaics. Very good at high concentrations as well. So you can concentrate the power like you do in concentrating solar thermal systems. So this, for example, is a parabolic dish, and there's a very small photovoltaic, triple junction photovoltaic cell at the center of the focus, and they work very well when you concentrate the sunlight up a couple of 100 times. So there's the 3 basic types of photovoltaics. But before we go to our laboratories, we work on a 4th type of solar cell, if you like. And the type of solar cell we work on is made from materials that are far more earth abundant than some of the materials I've just been talking about. In fact, the materials that we use are carbon-based semiconductors, or so-called organic semiconductors. And a couple of our organic semiconductors are shown down here. Any of you studying organic chemistry will know the different groups involved in these large organic molecules. But these organic molecules have the same sorts of physics as the materials I talked about previously, silicon and gallium arsenide and cadmium telluride. They are semiconductors and they can produce a photovoltaic effect. However, they produce a photovoltaic effect in much thinner layers than either the 50 microns of the cadmium telluride panels or in fact the 500 microns of the silicon panel. And in fact, our solar cells are only about 200 nanometers thick, which of course is about 100 times the width of a human hair. So very thin layers indeed. They're extremely simple, very simple solar cells indeed. Basically, they're a layer that produces the photovoltaic effect made of these organic semiconductors glued between 2 electrodes, one of which is transparent to let the light in, and the other is a reflecting metallic electrode to extract the electrons and extract the counter holes and generate the photovoltaic effect. Here's one that we made in our laboratory. This is an organic solar cell made from these types of materials, but it's flexible. It's made on a flexible foil, and it can be integrated into all sorts of different structures with flexible form factor. And in fact, these types of materials, because they are in fact ultra lightweight, plus they contain a low amount of embodied manufacturing energy, we think will be applicable and useful for many more applications than just sticking out in the desert or putting on your roof. And we're working on that as we speak. So what I'm going to do now is I'm going to cross over to a live feed to our laboratories at Singleton campus in Swansea. At our campus there, we have a special fabrication laboratory. It's an ultra clean environment. And Dr. Greg Burwell, who's one of our senior scientists, will tell you all about the type of science we do, and maybe we can have a live demonstration of the type of work that we do.
Hi everyone, I hope you can hear me okay. Everything coming through okay? Brilliant. So thanks for your introduction, Paul. I'm Greg Burwell. I'm a scientist here at the Center for Nano Health in the Sustainable Advanced Materials group with Paul. You may notice I'm wearing what's called a clean room suit, this blue suit here. This isn't to protect things that might be dangerous to me, but it's rather to protect the things I'm making from me. So this is a very, very clean environment. We're trying to minimize as much dust as possible. So in this lab, we'll work on semiconductors or other types of devices that we want to keep very, very clean. So this type of lab is called a clean room, and it has orders of magnitude less dust in here than outside. So what I'm going to do now, I'm going to share my screen and just give you a quick tour of the lab. You should see my camera, which I'm going to carry with me. Is that working okay? Can I just get a thumbs up? All right. So I'll just give you a pan around. So some of the equipment we have around here, lots of electrical testing equipment. And in particular, I want to show you the glove box, which is an environment where we keep oxygen and water away so we can work on the organic materials that Paul just mentioned. And over here, ready to do a demonstration for us is our colleague, Dr. Wei Li, who's going to show us how to cast some of these organic films. So if I go over here, what we'll show you is some different types of films that Wei has already cast. You can see some of the pretty colors resulting from the films. So these will be cast onto substrates, such that the one is he's holding up now. These will typically have a transparent conductive oxide like ITO as part of the device. He'll make sure they're extra clean, and he'll load them on to the spin coater. And Wei would have already prepared a solution with an organic material in some solvent. And the concentration of that solvent, together with the spin speed, will give us a very precise thin film thickness. So you should be able to see Wei casting a film now onto the substrate. And now we're spinning, and now you can see as it's spinning, it's coating the whole substrate quite evenly. This class of materials we call solution processable. So spin coating is one technique we use, particularly in research and development like this, but there's other ways of coating substrates with thin films, such as blade coating, that might be more suitable for larger areas. And it can be as quick as that. So when it's finished spinning, I think Wei will give us a look. And you can see that Wei used just a tiny volume of material to make this. So this is very efficient in terms of materials usage. And also these materials are non-toxic. I think we get a good image there of the nice cast film. Okay, thank you, Wei. And I think next we'd like to show you how we put the top electrode on these cells. What we're going to use is a thermal evaporation system. And this is a system that's capable of pumping down to very low pressures, to the -7 torr kind of range. It achieves that using a turbomolecular pump, you can see on the side here. And Wei is going to be loading up the evaporator. If I show you down here, what we can see is a shadow mask. So this will help us create different pixels on the substrate that Wei just cast the film on. And this is how we'd load it up. And with this, we'd get a couple different pixels for testing, which we'd get some relevant metrics for, like power conversion efficiency or fill factor. So we'd like to show you inside the evaporator now. So if you open up the hatch, what you can see inside here is different what's called sources. So these are not dissimilar to an old style incandescent light bulb in that it gets really hot. And when material gets really hot, you may know it'll evaporate. And it's the same for metals. So we would use small pellets of, for example, silver. I'm going to show you some examples of that. Some tiny silver pellets. And we don't need a lot of material because we're only doing very thin films of these metals. That would be loaded up, ready for evaporation. And then we would load the material upside down. Ah, okay. I don't know if we can load it right now, but it would be loaded upside down as so. And the reason we load it upside down is to stop any flaking onto the device, which may cause it to electrically short out. So I think now we're going to go to test a device that we made earlier. So I'm going to stop sharing at the moment and hand back to Paul. And if you give us a few minutes, we'll get ready to test the device for you live. Oh, I think you're still muted, Paul.
Okay, thanks, Greg. So that was actually a live feed. That wasn't pre-recorded, as you probably can tell. It looked a bit like the moon landing there, of the guys just beginning to prepare to make a cell. And I think the thing to emphasize is that these devices are very much lab-based devices. So they're very small, but clearly not much good for putting on people's roofs in that state. So what we do in our laboratories is we make these new materials and we test these new materials on very, very small platforms. And then we try and make them bigger and bigger and bigger once we've optimized everything in the structure and the way that we process the materials and the physics of the materials. And in fact, one tool that we use a lot to understand the way a solar cell works are these little simple models. This is called an equivalent circuit model. That is to say, since the solar cell is an electrical device, you can kind of represent it in broad terms using circuit elements such as resistors, and this is a diode circuit element, and this is a current source. So you can imagine that what you have is a solar cell, which is a current source when you shine light on it, and then it's got some sort of rectifying property represented by this diode. And then there are various resistances, a parallel resistance and a series resistance, which dictate ultimately how much current you can get out and how much voltage the solar cell can drop across a particular load. And in fact, there's a very, very famous equation called the Shockley diode equation, which explains in very simple detail, with very little physics actually, how the current and voltage generated by a solar cell can be represented in terms of some very basic fundamental properties. Importantly, you can see all these little voltages and series resistances and currents in this equation represented by the equivalent circuit. This is a very important factor here. It's called the ideality factor N, and it really tells you how perfect the solar cell is with respect to the ultimate current and voltage characteristics, how much losses you get via these resistances, for example. And the guys are going off to another laboratory now in order to measure something like this. This is the so-called current versus voltage characteristics of an experimental solar cell. In fact, it is one of the solar cells that Wei was making in the laboratory. He made it a couple of months ago, but pretty much exactly as you saw there. And what we're plotting, as I say, is the current versus the voltage. And there are some important quantities. The first thing to notice is this curve here, this black curve. This is the so-called current voltage characteristics in the dark. So when we don't have this, this light current source, this light induced current source, okay? So this is what it looks like in the dark, and it basically looks like a simple diode that you might have seen in your A-level physics. When we shine light on it, we suddenly get current. And in fact, this solar cell generates 25 milliamps per centimeter squared. And this current, as we step through the voltage, comes to a point at which the cell generates the maximum current voltage product, and we call that the maximum power point. And in fact, every photovoltaic module that you've got on your roof and every photovoltaic module that's in a big solar plant has electronics which balance the cells within each of the modules at this so-called maximum power point. And so the critical characteristics, this particular solar cell's got a power conversion efficiency of 15%. So just 100 nanometers of that organic semiconductor can produce 15% power conversion efficiency. When you consider that a silicon module produces 25%, it's not far off. And there's some important quantities here. This thing called the fill factor, which is how perfect this light-induced current voltage characteristic is to square, is a very important quantity. And this thing here is a so-called short-circuit current density, which is the maximum current that can be generated, and the open circuit voltage is the maximum voltage that can be generated. So this is indeed what we measure on each of the solar cells that we produce in our lab. And we have to do this under very standard conditions. And I mentioned the AM1.5 air mass index a bit earlier. And in fact, in our lab, we have an artificial sun that gives us exactly AM1.5 mass index of radiation. And we're going to go back to the lab now, and we're going to see Greg scanning through a solar cell that was made earlier today.
Hi again, everyone. So I'm out of the clean room now into our testing laboratory. Just going to cut to Wei again, who's going to show us a measurement. So this is our solar simulator. First of all, he's going to position a device. So this is the sort of thing we were making earlier in the lab. Now it has the metal contacts evaporated on top. That will have a shadow mask on as well, so we're accurately defining how much light is going through to the device. That's very important for the calculations we do to see how efficient they are. We're going to turn on the bulb now, which, as Paul just mentioned, will replicate the spectrum from the sun, which we may have calibrated using a reference cell. And then we're going to do a sweep of this device to see its electrical characteristics. Let's just make sure I got a good feed for the screen for you. There we go. So now we can see that diode curve coming in. As we can see on the side here, it's already giving us some parameters of how these cells are performing. So you can see on the side we're measuring PCE, which is power conversion efficiency, and fill factor, and other important parameters like the short circuit current, open circuit voltage. These are all parameters we'd use to understand the device physics better and further develop the materials.
Okay, thanks, Greg. Brilliant. Thank you, Greg.
Okay, I'll see you soon.
Okay, so a couple of things to emphasize there is that, you know, this is what we do on a daily basis. This is how solar cells are developed. This is how the first silicon cells were made. This is how the first cadmium telluride cells are made. And so in a couple of years' time, with a bit of luck, if we continue working like this, and many other researchers working in this field as well, you'll see plastic solar cells that are integrated in the fabric of cars, that are maybe in the wings of aeroplanes, or maybe driving small local power sources for Internet of Things. So these are the things that we can envisage. The other thing I just wanted to make clear was that, you know, during these very difficult times that we've had during COVID, we have managed to keep going. Our research has reopened, and we are working safely. And you could see the guys in the laboratory there practicing all the social distancing measures, full protective equipment as well. So I just want to thank the guys for you know, for all their hard work in getting our labs up and running. Swansea University is open for business, it would seem, at least for our research. Okay, so I'm going to start drawing things to a little bit of a close now by looking at some much larger scale photovoltaics. And the reason that I suppose PV is a bit more popular, if you get, than solar thermal, is it's much more versatile. Photovoltaics can be integrated into the fabric of buildings, for example. We see these on the roofs of houses or sheds. This is a farm shed, for example, in the United Kingdom. This is a conference centre roof in Queensland, which is silicon photovoltaic panels integrated into it. So it's far more suited to both local small-scale generation and, in fact, the really big stuff. This is a plant in southern Spain, which is hundreds of megawatts. So this is kilowatts of power. This is hundreds of kilowatts of power, and this is megawatts of power. And in fact, this is a little field that we built at our university in Queensland, one of our agricultural campuses. And this is, of course, where, you know, you talk about solar farms often, and the integration of agricultural endeavours, the growing of food, the raising of livestock, with the generation of electrical power, all co-located in the same field. And in fact, this site, which is just west of Brisbane at a place called Gatton, which is the university's agricultural campus, is the only place in the world where you have all sorts of different technologies that are comparing against each other on the same site. These little things here are two-axis tracking photovoltaic panels, and they track the sun minute by minute as soon as it comes up in two axes. So both the tilt and the azimuth, so they're always staring directly at the sun. And these things are tracked actively. That is to say, they have an intelligent little photodetector that always optimizes their position with respect to the sun. These guys here are completely fixed. So they sit on fixed rails. And in fact, since Brisbane is 27 degrees latitude, they sit facing 27 degrees tilt, but facing the northern hemisphere. And just over here at the far end of the picture is a field of so-called single-axis trackers, and they track just in one dimension, that is to say east-west, as the sun goes over the Earth during the course of the day. So you have two-axis, single-axis, and fixed, and this is the only place on the planet where we're comparing all of those things directly. These arrays, you can download the data from these arrays dynamically. There's a website called UQ Solar that I'll give you on the resource. And if you're really interested in downloading minute-by-minute solar data from a real working solar plant, then you can do that via the UQ Solar website. And I've got some data from you. I plotted this earlier today, and this data shows you the power that's being generated by each of these types of array, the fixed, the single axis, and the dual axis, as a function of time. And what I did was, from the historical data, I picked a day, which was the 20th of February 2020 this year, which was such a perfect solar day that it almost gave us textbook-like photovoltaic output. And you can see what's happening is that these three arrays, the blue one is the fixed, the orange one is the single axis, and the gray one is the dual axis. And you can see that at around about 5:30 in the morning, when the sun comes up in Brisbane in midsummer, which is February, the two axis and the single axis immediately start turning on. And the fixed axis, of course, because it's not looking at the sunlight directly at that point in time, takes a little time, and it reaches its peak, not surprisingly, around about 12 noon, because this is nearly midsummer. And also you see the difference in shapes of these profiles as a function of time during the day. And from these shapes and from the total amount of power, we can calculate what the capacity factors are. And it turns out that in Brisbane, with this type of technology, that fixed gives us about a 20% capacity factor, single axis about 23, and dual axis about 24. Now, if you took this data on face value, you would say that you would always install dual axis tracking photovoltaic technology. but it turns out that to do dual axis tracking is very expensive indeed. And in fact, these things have got large 3-phase independent motors, which you have to take into account. So it's very expensive to do this thing. And it turns out that the sort of crossover between the capacity factor and cost is these simple single axis trackers. And more people around the world now are building these very simple single axis trackers to get the maximum possible capacity factor, the maximum amount of energy that the plant produces over its lifespan, given that these things have to last for 20 or 25 years out in the field. So there's some nice data from down in Brisbane. And that brings me to the kind of final bit of what we want to talk about now, and why the sheep is in the webinar in the first place. Well, that dual axis tracking field that I showed you in Brisbane, we decided in about 2015, 2016, we were having trouble keeping the grass down, actually. And it was costing us money to mow the grass all the time because the grass got very high and started shielding the panels. And somebody came up with the bright idea of putting 10 sheep in the paddock with the 2-axis tracking. And this was a good idea. And it turns out that these particular sheep, and there's Dolly sitting there again, these particular sheep, which are sort of hardy Australian outback sheep, were absolutely perfect for cutting the grass, for keeping the grass low, and also keeping the amount of dust down. They ate just enough grass to keep the grass low, but not too much grass, such that they produced a lot of dust. And a lot of dust, of course, means that you get dirt on the solar panels, and dirt on the solar panels mean you get reduced capacity factors. So this news was picked up by the news media in Australia, and it was all over the newspapers. And in fact, there was an article written by the Australian Broadcast Corporation, which was entitled "Hungry Sheep Help Save Money at University of Queensland Solar Research Farm." And there was a quote by the manager of the farm along the lines of, well, we found that the sheep are really enjoying being in the solar panels. There's great feed available for them. And the fact that we have solar panels there, it also provides great shading opportunities for them. So it turns out it was a win-win for the sheep, and it was a win-win for the solar plant. And so now it's common practice to put sheep in solar plant fields, because you can, of course, produce wool at the same time, and it helps keep and maintain the solar plant. So that's why sheep and photovoltaics are linked. And it's a nice little story of how you can integrate old industry, as in agriculture, which is very, very important, with the new industry of clean energy. So before I leave, I wanted just to point you to another little resource, which I won't go into now, because we're getting towards the end of the webinar. But the University of Sheffield, up in the north of England, has got this fantastic resource called Solar Sheffield. And the resource that I showed you on Solar Ninjas is sort of a global context of what one can do with renewable resource. And the Solar Sheffield resource is very specific to the United Kingdom. So they have this tool called the Profiler, where you can input your postcode and set the parameters like I showed you on Renewables Ninja, and it will give you an accurate energy yield calculation of a solar photovoltaic system that you put on your roof. So if you ever want to put a PV system on your roof, the first thing you have to do is understand whether or not it's going to make you any money, or it's going to generate very much electricity. And so this tool now is being used by the industry. It was developed by the guys at Sheffield and gives you a fairly accurate prediction of how much energy yield. So I think we're probably getting through the seminar now. It's coming up on 2 hours. And so I'd like to give us 10 minutes for some Q&A. So I'm going to hand over now before we finish up, I'm going to hand over to James again, to maybe do a little bit of a Q&A. But before we do that, I just want to say some thanks and kind of give you some take-home messages. And then we can launch into the Q&A. So I think the key take-home message from the climate bit of this webinar is that we really are in the midst of this hothouse effect of the global warming. And I think we're well on our way 2 degrees, as James said. And that is largely driven by human emissions in the industrial era of these greenhouse gases. Different greenhouse gases have different overall impacts. And through Arrhenius's equation, we saw that they're cumulative. So if you have an effect produced by methane or an effect produced by carbon dioxide or water, they add up. And so the more we pump different greenhouse gases into the environment, the more we perturb the Earth's climate in that regard. But the news is improving, and we have the 2050 target by the UK government for zero carbon, and we have the big penetration now of wind, solar, biomass and hydro making in the electricity system in the United Kingdom. We saw that we were generating 30% today of renewable electricity from the resources that we've got in the United Kingdom. Okay. We talked about solar power in true flavors. We talked about the thermal bit where we convert and absorb the thermal radiation of the sun. And we talked about photovoltaics, which is the direct conversion of photons to volts via a semiconductor. The average capacity factor for a photovoltaic system in the UK is about 11 to 13%, but we have much better wind resource, and particularly offshore wind resource gives us those capacity factors up around 40%. We showed you our labs. Where new PVIC technology is coming online right in front of your very eyes. And we're working on this type of plastic technology that's extremely lightweight, we hope very low cost, and also can be integrated into a far larger range of applications such as mobile transport sources, and maybe aerospace and transport and terrestrial transport as well. And that's what we're doing at Swansea alongside many of our other colleagues at British and global universities. So with that, I'll just thank a few people, the comms team at Swansea, who put this together, James for emceeing and QAing and doing the quiz, for Drs. Burwell and Lee back at Swansea, and Professor Hans at Swansea as well, Swansea Physics, who set this thing up in the first place. I'd also like to acknowledge my colleagues in Australia and up in Sheffield who are doing absolutely fine work in giving public information forward on the performance of solar systems, which is very, very important. And finally, a quick thank you to the funding councils. We're funded by the European Regional Development Fund for our work at Swansea and the Welsh Government via this programme, the SAM programme. And we're also now funded by the UK Research and Innovation, which is the UK's main funding agency. And if you want to find out any more, then please check us out on advancedmattersswansea.co.uk, where you can see what sort of work we're doing. And I'll leave this up while maybe we QA for a bit. These are the resources that we've used in putting this webinar together. They're all publicly available sources, and all copyrights, etc., have been noted where the source was used. Thank you very much. And over to you again, James.
Okay, thank you very much, Paul. So as we said at the start, this webinar is recorded. It will be available along with the slides, I believe. And certainly all of these links, and that will be at the address that I am just posting in the chat right now. So Swansea AC UK /physics /a quick guide to undergraduate physics, where we have collected some resources that we think will help with the transition from school to university, and it includes some previous webinars. I'm particularly happy to see this one from Paul because I'm an experimentalist, and I felt that our theory groups were particularly well represented so far, quantum gravity, particle physics, so it's great to have something from the applied side. Okay, so we have a couple of questions. The first one, Paul, is how efficient is your version of the solar cells? So it's more about the ubiquity of how you could deploy these things, I think. Shall I answer, Paul, or?
I can take that. So the particular cell that Greg was showing there has got a power conversion efficiency of around about 15%, but that's at a lab scale. And the problem is that when we try and make these things bigger, so that they can generate enough electricity to be viable, like a silicon or cadmium telluride panel, they lose power. There's some problems with so-called scaling physics, taking something from that tiny little couple of centimeters and making meters of it. And we're doing a lot of work in understanding that, and we're making quite a lot of progress. But when we make big cells out of these things, they lose about a third of their power. Okay, and we understand the physics of that, but the materials innovations haven't caught up with our understanding of the physics, and that is a ubiquity throughout all of physics, is that we often understand the physics first, and then we do the engineering and the material science to make the materials to make the physics work. How far off are we from seeing this type of technology? Well, the world record at the moment for that type of technology is 18% in a lab scale cell, and about 13 or 14% in a larger area. So we're getting there, and I'm not going to say it's going to happen overnight, but there are certain very distinct advantages in terms of what we're trying to do here, and they you know, they're absolutely centered around the use of low amounts of energy to make the thing in the first place. Otherwise, what's the point? And our ability to use quite low cost and very sort of earth abundant materials which are non-toxic to actually make the solar cells. So maybe you'll see these plastic solar cells integrated into, I don't know, building fabric, cars, airplane wings within the next decade. We certainly hope so. And we think there's potential for that. Otherwise, we wouldn't be wasting our time doing it. So I think that's probably a good point. Alan James?
Okay, so are there any ideas as to why the global temperatures did not rise much in the 1970s? So on that, I would say it's very easy to get distracted by the noisy details where it's absolutely clear what the overall trend is. In fact, if you look at year on year, then sometimes it goes up for 5 years, sometimes it goes down. But overall, the trend is, we've got a very simple model to explain it, and the trend is obvious. So I think these sorts of, they're interesting, but it's really a problem for climate physicists and understanding the weather patterns and all sorts of atmospheric phenomena, whereas the overall trend and the problems that we have to fix are absolutely clear. Sometimes these trends are picked upon by people who are not quite honest in why they're picking on those trends, cherry picking the data. The overall trend is extremely clear and much less a function of the model, actually. So you can look at the detailed models, and then Paul showed in his early slides some trends, and there was a bit of, there was a range. But as you look further into the future, all the models come to broadly the same conclusion.
Okay, more of that, James?
Why do we not see cars with solar panels on the roof yet? Yes, why, Paul?
Okay, that's a really intelligent question from somebody, and it's about power to weight density. So in the limit, what we want is to have an electric vehicle, yeah, that's got a very efficient battery, which can harvest electricity from all sorts of places. So maybe it can drive over a road which has got inductive charging, yeah, on a smart road. Maybe it can harvest solar power and turn that into electricity and drive the motor and also charge the batteries. That would be great too. And that kind of vehicle is the kind of nirvana for the future of transport. But at the moment, the types of technology that I'm showing you, for example, the silicon-based technology and the gallium arsenide-based technology and the cadmium telluride-based technology, they either have not got a sufficient power per unit weight to make it sensible to put it into a transport vehicle. Obviously, if you put a very heavy solar panel on something, then it actually probably takes up more power to drive the vehicle with the extra weight than it's producing, or it's prohibitively expensive. So I showed you there the really, really high efficiency triple junction epitaxial technology, and that has got the highest power density of any photovoltaic technology at the moment. It's roughly 2 kilowatts per kilogram is the power density, and that's the world record, about 2 kilowatts per kilogram, held by a company called Microlink Devices. But unfortunately, those cells, although they'll be perfect for integrating into cars and other transport vehicles, are prohibitively expensive. So basically, either you've got a cheap technology which doesn't have the power density, or you've got a technology which has the power density but is too expensive to integrate into something like a car, which essentially is a consumer product, right? You know, you want to buy a car for £20,000, you don't want to add another £10,000 for putting a few solar panels on it. So that's the dynamic, and that is actually one of the sweet spots. I'm glad you asked the question, because that's one of the sweet spots that we think we want to try and address in terms of this new lightweight, high power density, low cost photovoltaics that's going to be needed for transportation sector.
So there's a question of whether the specific technologies at Swansea were implemented throughout the UK. Would it solve the energy issue? I'm not really sure which energy issue. I mean, it looks like we are adopting a diverse approach in this country, which includes a range of renewables with different dependencies. Some work on a windy day, some work when it's been raining a lot, some work when it's sunny, and nuclear, and sharing with through links onto the continent. So Paul's pointed out some specific instances where the technologies he's working on would make a big difference, but not necessarily to grid scale energy generation. That's not really what you're targeting. No,
we're not. And James, I think it's I mean, it's a very good question, and it's one we get asked a lot. Is, you know, if we covered the whole of Britain with photovoltaic panels, would that solve the problem? No, it wouldn't solve the problem. And the first thing that we think about is this intermittency problem. If you have a combinatorial approach, where, for example, you deploy a large amount of wind resource, and generally speaking, wind and solar are sort of kind of one upon each other, right? Generally speaking, when the wind is blowing hard, it's you don't get a lot of sun, and when the sun is out and it's nice and shiny, then the wind is usually quite low. Not exclusively, but you can begin to think about a jigsaw puzzle where you look at the system capacity factor, so the capacity factor of the whole system, and that maybe is underpinned by so-called baseload power like nuclear. There's no doubt, and although I'm a renewable energy researcher, I understand the need for us to also have low emissions, so-called baseload 100% capacity factor power, and that at the moment in Britain is coming from closed cycle gas turbine, which is actually quite an efficient way of burning fossil fuel if we are going to continue towards this low emission trajectory that we need to be on. So you have to take this very balanced view of it, and in the end, what we're going to see is a transition which brings more renewables in, less fossil fuel going out, and some baseload of nuclear sitting on the top of it. And that's going to be what our energy transition looks like over the next 50 years. And I think any commentator that understands the technologies will say that.
There is reason to be optimistic.
There's every reason to be optimistic. And I think what you saw with GridWatch is hugely optimistic.
Can I just add one thing on the solar cars? To the person who asked that question, there's a race called the World Solar Challenge, in which they build and race solar-powered cars, and that's one way that they develop these technologies sort of in the real world, obviously in kind of an artificial environment with a view to reduce or improve power to weight, this sort of thing. So
there's also interest in the aerospace industry. So Airbus have this Zephyr thing, a unmanned air vehicle which is solar powered. I think it's got some battery backup, but the idea is it's a plane, 25 meters or so wingspan, which flies just using solar power. So there's a lot of, it's not going to be in domestic cars for a while, if it is ever, but there's other applications where vehicles really are solar powered.
Yeah, that Zephyr project, James, has got the ultra lightweight triple junction epitaxial technology on its wings.
So I think we're about ready to wrap up. If you haven't gone to that link already, I'd strongly encourage you to check out this Without the Hot Air book. Fantastic, especially as a physicist trying to understand these issues. So I think we're done. You're muted, Paul, you're muted.
Well, I'll say goodbye. Thank you for listening, everybody, and staying with us. I know a lot of you have stayed with us, so I hope you enjoyed it. You can provide any feedback as well to James, and I hope you all learned something and enjoyed it very much.
Okay. Thank you all. Goodbye.